Hello everyone, this is lecture 15, derivative of exponential and logarithmic functions. The learning objectives of this lecture is to find the derivative of exponential and logarithmic functions. In addition to that, we will learn a new differentiation technique. It's called the logarithmic differentiations to find the derivative of some more complicated function. First of all, let me go back and revisit the idea of derivative of exponential functions. So we learned before that if you have a natural exponential functions, f of x equal to e to the x, the derivative of this function is f prime of x equal to e to the x. So the derivative of e to the x is e to the x itself. In addition to that, if you have the general exponential functions of the form a to the x, the derivative of this function is f prime of x equal to ln of a times a to the x. Now we're going to apply this formula into some example. Let's consider example 1. So in this example, I want to find the derivative of the following functions. Right. So in part A, I have the functions f of x equal to e to the x minus x. So the derivative of this function is f prime of x equal to e to the x minus x prime. So as you remember, the derivative of the difference is the difference of derivatives. So therefore, this derivative becomes e to the x prime minus x prime. So e to the x prime, as you can see earlier, the formula, the derivative of e to the x is e to the x itself. And the derivative of x is just equal to 1. So I have this is minus 1. Now let's move on to the second problem. I have the function g of x equal to 2 to the x. Right. Again, if you apply the derivative of the general exponential functions, but in this case, the base is equal to 2. Therefore, the derivative of the function is ln of 2 times 2 to the x. Now let's move on to a little bit more complicated problem. Problem C. In this problem, I have the function g of x equal to 5 to the x plus x to the 5th power minus 5 times e to the x. Right. So the derivative is g prime of x is equal to 5 to the x plus x to the 5th power minus 5 times e to the x prime. Right. Again, derivative of a sum is the sum of derivative, and derivative of a difference is difference of derivatives. So therefore, I could be able to obtain g prime of x equal to 5 to the x prime plus x to the 5th power prime minus 5 times e to the x prime. Right. So as a quick reminder, the 5 in this case, the constant multiple. So when you find the derivative of a constant multiple multiplied with the functions, then you just kind of put the constant multiple aside and just take the derivative of the function itself. Okay. So for this derivative, the first term will give me ln of 5 times 5 to the x. For the second term, you can apply power rule, which give me 5 times x to the 4th power. And for the last term, derivative of e to the x is e to the x itself. So I get minus 5 times e to the x. Let's move on to the last problem in this example. So for D, I have the functions f of t equal to 7 to the t minus 6 times square root of t plus 8 times e to the t. Before taking the derivative, what I could do is I could change the square root of t into a power function, which is, it can be rewritten as t to the 1/2. So I have 7 to the t minus 6 times t to the 1/2 plus 8 times e to the t. And as you take the derivative, you get the derivative of 7 to the t, give me ln of 7 times 7 to the t. And negative 6 in this case, the constant multiple. So when I take the derivative, I'm going to put the 6 to the side. and take the derivative of t to the 1/2, right? So derivative of t to the 1/2 is 1/2 times t to the 1/2 minus 1. And for the last term, again, 8 is a constant multiple, and the derivative of e to the t with respect to t, it's just e to the t. So for the last term, I get 8 times e to the t. Now let's simplify the answer a little bit. So the first term remained the same. So I have ln of 7 times 7 to the t. For the middle term, I'm going to simplify the 6 and the 1/2, and I get 3 times t to the negative 1/2 plus 8 times e to the t. Now let's move on to the derivative of logarithmic functions. You learn in pre-calculus that for logarithmic functions, you have to identify the domain of the logarithmic functions. So in this case, before considering finding the derivative of ln of x, we have to define that x has to be greater than 0, which is the domain of the natural log functions, right? And the derivative of the natural log function is given as, so in this case, y prime equal to 1 over x. And in order to find the derivative of the general logarithmic functions or the log functions of base a's, we consider y equal to log of base a of x and write that in terms of an exponential function. So in this case, you have a to the y equal to x. We could be able to do this because remember that exponential functions and logarithmic functions are inverses of one another. So that means instead of y equal to log of base a of x, we're going to write a to the y times x, right? And we use implicit differentiations, and we learned before to find the derivative of the log of base a of x. So what I can do is I'm going to take the derivative on both sides of a to the y equal to x. I get d dx of a to the y equal to d dx of x. On the right hand side, should be straightforward, right? D dx of x is equal to 1. The derivative on the left is equal to ln of a times a to the y. But remember chain rule, right? You take in the derivative of something in terms of y, but with respect to x. So that means when you take the derivative of the left-hand side, not only that you have ln of y times a to the y, this is the derivative of the exponential functions, you still have something called the chain rule, right? And you have to take the derivative of the inside function, and the inside part of the function is y. You still have dy dx in this case, and you set this equal to 1. Now you solve for dy dx by dividing both sides for ln of a times a to the y. This gives me 1 over ln of a times a to the y. However, we are not done yet, right? Because the result is in terms of y, but we don't like that, right? We want the answer in terms of x only. So what we do is we substitute y equal to log of base a of x back into the result. Okay, so here's what we do. We have dy dx equal to 1 over ln of a times a to the power log of base a of x. It's a little complicated for the denominator, but if you notice that a to the power log of base a of x is actually a cancellation property, which will give me just x. Right? That part of the properties of the logarithms that we learn in pre-calculus, that exponential function and logarithmic functions are inverses of one another, and in a way it's not mathematically correct to say, but it's more convenient for us to understand the procedure that exponential function and logarithmic function in this case kind of cancel out, and you're left with just x, right? So therefore the final answer is dy dx equal to 1 over ln of a times x. So therefore, the formula for the derivative of logarithmic functions with base a is if you have y equal to log of base a of x, the derivative of this is y prime equal to 1 over ln of a times x. In case of more complicated functions, more complicated inside part of the function, instead the inside part of x, we have a more complicated inside function. So that is if we have y equal to log of base a of some function g of x, then the derivative is y prime equal to 1 over ln of a, because of base a, right, times g of x, which is the inside part. Now, because the inside part is more complicated, you have an inside function, you need to multiply with the derivative of the inside function. So this is the chain rule for logarithmic functions. There are a lot of formula for the logarithmic functions, but let's try some example and see how the formula get used in this example. For example 2, I want to differentiate y equal to ln of x squared plus 1. When you see this problem, you may consider the chain rule. Right? So the outside part is the natural log functions, and the inside part is x squared plus 1. So you can apply the chain rule for logarithmic functions. So that is y prime is equal to 1 over ln of e, because you have e is the base in this case, times the inside part, which is x squared plus 1, then multiply with the derivative of the inside function, which is x squared plus 1. Right? And remember, ln of e is an identity. Ln of e is always equal to 1. And we have 1 over x squared plus 1 times the derivative of x squared plus 1, and the derivative of x squared plus 1 is 2x. Okay, and if you can rewrite this functions, you have y prime equal to 2x over x squared plus 1. Now let's move on to the next example. Now find the derivative of the functions ln of x cubed plus 3x minus 4. And again, the outside part is the natural log part, or the log of base e in this case. And the inside function is x cubed plus 3x minus 4. So the derivative is y prime equal to 1 over ln of e times the inside part, which is x cubed plus 3x minus 4. And at the end, you multiply with the derivative of the inside functions, which is the derivative of x cubed plus 3x minus 4. Right. And again, in the denominator, ln of e is equal to 1. So you still have x cubed plus 3x minus 4. Now we have 1 over x cubed plus 3x minus 4, and multiply with the derivative of x cubed plus 3x minus 4. Right? You get the derivative of x cubed is 3x squared. The derivative of 3x is just 3, and the derivative of 4 is equal to 0. So this is what we got. Right? If you want, you can simplify the functions or the result a little bit by taking 3 as the common factor on the numerator. So you have 3 times x squared plus 1 over x cubed plus 3x minus 4. So we could be able to go from this step to this step is because the idea is, this is just a side note. You have basically two fractions. One is 1 over x cubed plus 3x minus 4. The other one is 3x squared plus 3 over 1. Right? So the top multiply with top, and the bottom multiply with bottom. So that's why you have 3x squared plus 3 over x cubed plus 3x minus 4. And on the numerator, I take 3 as the common factor. Now let's move on to example 4. Again, in this example, I want to find the derivative of the functions ln of sine of x. So the outside part is natural log functions and the inside part is sine of x. So the derivative of this function is y prime equal to 1 over ln of e times sine of x, which is the inside part. And at the end, you multiply with the derivative of the inside functions. Again, ln of e is equal to 1. This gives me 1 over sine of x. And the derivative of sine of x is cosine of x. For this, I would like to combine these two terms together. So remember, I have two fractions in this case. One is 1 over sine of x, and the other one is cosine over 1. So top multiply with top, bottom multiply with bottom, and I have cosine of x over sine of x. And you can leave it right here, but some of you, if you remember the trigonometry ratio, cosine of x over sine of x is the cotangent of x. Okay. Now let's move on to example 5. In this example 5, again, differentiate the function f of x equal to square root of ln of x. The difference between this problem and the previous example is that in this problem, the inside function is the natural log functions. How could I see that? If I rewrite square root of ln of x as ln of x to the power 1/2, you can see that ln of x is the inside part, the inside functions, and the outside part is the power function, power 1/2. Right? So what we do is, again, apply chain rule. The derivative of the chain rule is the derivative of the outside function, multiply with the derivative of the inside functions. So what I get is f prime of x equal to 1/2 times ln of x to the 1/2 minus 1. So this is the derivative of the outside part. Multiply with the derivative of the inside part. So the derivative of ln of x is just 1 over x. Now, if you go back to the formula, you will see that is the case. Right? So I get 1/2 times ln of x to the negative 1/2 times 1 over x. Okay. Now, finally, let's move on to the last example in this category. Right. So I would like to differentiate the function y equal to log of base 2 of 3x plus 1. Remember, in this case, the base is equal to 2. Right. So the derivative is y prime equal to 1 over ln of 2 times the inside part. And then at the end, multiply with the derivative of the inside function. So derivative of 3x plus 1 is just 3 because the derivative of 3x is 3 and derivative of 1 is 0. So I get 1 over ln of 2 times 3x plus 1. And here I multiply with 3. So I get 3 over ln of 2 times 3x plus 1. Okay.